spaces and Frobenius groups of finite Morley rank. So Katrin, you can start.
Yes, thank you very much. I think you can see my screen and you see when I move my slides, right?
Yes, exactly.
Okay, very good. Okay, first, let me really thank the organizers for the opportunity to speak here. It's really a great pleasure to speak in Udi's birthday conference. I first met Udi in 1994 when he gave a talk in the ASL spring meeting in Notre Dame about his Model Lang result. And I remember people leaving the talk and thinking, what? Did he really prove this? So it was really a fantastic experience. And then coming to Jerusalem as a postdoc was very nice. So I'm really happy to and honored to be giving a talk here. And so my title is Mock Hyperbolic Reflection Spaces. And let me start with the definition. It's not a definition that you're supposed to know. It's some kind of natural point line geometry interaction with reflection groups. So this is joint work with my student Tim Clausen, and this is where we introduced this notion. And the term mock hyperbolic reflection space is a bit clumsy, but all the shorter terms that we could come up with already were taken by some other concept, and so we didn't want to create doubles. So anyway, what's a mock hyperbolic reflection space? It's a point line geometry together with a group of automorphisms and the conjugacy class of involutions, such that any 2 points are contained in a unique line. Any involution has a unique fixed point in the point set, and any fixed point corresponds to some involution that fixes it. And the main point that goes back to Bachmann is the following. 3 points in this space are collinear if and only if the product of the corresponding involutions is again an involution. And furthermore, we want that for any 2 points, there is a unique involution swapping them. And if you have 2 lines in your geometry, 2 distinct lines, then there should be at most 1 involution swapping these 2 lines. And I already mentioned this kind of geometry based on involutions goes back to Bachmann. And the name comes from the fact that one example of such a geometry is the hyperbolic plane with the action of PSL2 over the reals. But of course, also if you just take the real line and you take all the reflections around the point in the real line, this will be an example. It's easy to check. There, a product of 2 such reflections is a translation on the real line. Of course, the automorphism group is the affine linear transformations. So this is a sharply 2 transitive group. So in general, you get other examples from sharply 2 transitive groups. And actually, you also get examples from bad groups in the sense of Churlin. And those who know bad groups know that these groups don't have involutions, but I will explain in a moment how these groups also give rise to such reflection spaces. So as I said, the real line is an example of that with the point reflections. And this is actually the motivation that we started looking at these geometries, namely we were looking at sharply 2 transitive groups, and a sharply 2 transitive group is a group acting transitively on pairs of distinct elements such that there's a unique element in G taking 1 pair of distinct elements to any other pair. And in the context, in the algebraicity conjecture, in the Churlin-Silver conjecture, the conjecture states that any sharply 2 transitive group of finite Morley rank should be of this form, K semidirect multiplicative group, so exactly the affine group AGL1 of K for some algebraically closed field K. And if you look at this conjecture, it has 2 parts, namely, first of all, you want to know that any sharply 2 transitive group of finite Morley rank splits, that is, has a normal subgroup here in this case. It need not be a field or an algebraically closed field, but in any case, if it splits, it's of the form n semi-direct n star for some near field n. So a near field is an algebraic structure similar to a field, but you have all the same rules as in a field, but only one distributive law that holds. And it's easy to see that if you have a field with only one distributive law, you can still construct a sharply two transitive group exactly in this form, because you only need one distributive law to make the action work. And then the second part, of course, is that you want to know that any near field of finite Morley rank is algebraically closed. And this result was recently proved by Altenel, Eiche Bergmann, and Frank Wagner. And for the first part, until a few years ago, there were no other sharply two transitive groups known than those that were of this form. But so recently, in joint work with Ilya Rips and Yoav Segev, and then with Ilya in characteristic 0, we actually produced non-split sharply two transitive groups that do not arise from near fields. So it would actually say something extra if for finite Morley rank this holds. It's not just a statement about near fields, but it's really a statement about groups. So as I said, the motivation comes from sharply two transitive groups, but what we have to show is that the splitting holds. And for the splitting, we might go to a broader context, namely we can look at Frobenius groups. And Frobenius groups are transitive groups with trivial two-point stabilizers, so transitive but not regular groups. And so here it seems that you have to talk about a group action, but you can translate this into a purely group theoretic formulation. So Frobenius group is a group together with the point stabilizer H, if you think of it that way, and you want that it's non-trivial, so the group is not regular. And you want that two-point stabilizers are trivial, which means that the intersection of two stabilizers should be the identity, but if the group action is transitive, all the point stabilizers are conjugates. So this condition here translates exactly into having a group with a non-trivial Marr-normal subgroup H. So Frobenius showed in the beginning of the 20th century that finite Frobenius groups are always split. And by the way, also, I mean, of course, this covers finite sharply two transitive groups. They were known to split even before that. But in the finite case, they all split. And in fact, if there were non-split Frobenius groups of finite Morley rank, then this would actually contradict the algebraicity conjecture. So the conjecture that the Frobenius groups of finite Morley rank should split. Now, recently with Simon André, we produced simple sharply two transitive groups of characteristic 0. And what's strange is that we don't know whether these groups can actually have finite Morley rank. I mean, normally you don't just accidentally produce a group of finite Morley rank, so I think it's safe to assume that they don't have finite Morley rank, but we haven't yet found an obvious reason. So,
Katrin, can you remind what is characteristic 0 for a group?
Yes. So if yes, it's the permutation characteristic. So if you have a sharply two transitive group, then you have, of course, lots of involutions in this group, because for any pair of points you can swap them, and swapping them twice fixes them. So it must be the identity. So it's an involution. So if you look at two involutions, either, well, obviously they're conjugate, because you can take this pair that swap to this pair that swap. So the involutions form a unique conjugacy class. So either they have a fixed point, all of them, or they don't have a fixed point. So if you think of the affine line, then the case where involutions don't have fixed points are the ones where the characteristic of the field is 2. So you say that the characteristic is 2 if involutions have no fixed point. And if involutions have fixed points, then the characteristic is defined to be the order of the dihedral subgroup generated by the 2 involutions, because that corresponds actually to the translations and therefore to the characteristic of the field that you see there. So characteristic 0 means involutions have fixed points and any 2 involutions generate an infinite dihedral group. So, and they all contain subgroups of the form AGL1, so the affine linear transformations over a field of characteristic 0. So, for example,
sorry, the characteristic is a prime, or can it be any integer? Or?
It has to be a prime, yes.
It has to be a prime, okay.
Yes. So, and the degrees, I mean, the definition of the characteristic, if you look at the affine transformations, it gives you the characteristic of the field. This is exactly because the product of 2 involutions is a translation in the projective line, in the affine line.
Yes.
Okay, so this would be a place to look if you hope that this conjecture might be wrong. So check whether these groups actually have finite Morley rank. So for Frobenius groups of finite Morley rank, there's not too much known actually. What is known is that it suffices to consider connected Frobenius groups, so ones without definable subgroups of finite index. And one can also assume that the Frobenius complement H is connected because it's known that if H is a finite group, then the group splits. Also, if the group is solvable, it splits. There are some special cases that are known, but in general, not too much is known. But what follows from the, from the setup is that there are 3 classes, 3 types of Frobenius groups as far as the involutions are concerned. You can have an involution in the point stabilizer that corresponds to the characteristic of the field being odd. So, and in this case, you call the group of odd type. G could not contain any involutions, then it's called degenerate type, or the fixed point free element could contain involutions, and that corresponds to the even type. Now, the even type groups of finite Morley rank are more or less classified, so that leaves the odd and the degenerate type to look at. And in this context, we can look at Frobenius groups of small rank, and a Frobenius group is called full if the conjugates of H cover the group. Of course, you see that in a finite group, this can never happen. It's also an easy exercise for undergraduates to see that in a finite group, you never have this. But apparently, it's not totally clear whether this can actually happen in infinite groups, but it seems that Olshansky maybe produced an example of this. But in any case, a full Frobenius group is of this form. And it's known that a full Frobenius group of finite Morley rank does not contain involutions and cannot split. And now we can phrase Fréquent's result about bad groups in the following form. There is no simple full Frobenius group of Morley rank 3. This is a precise translation of his result in this context. He proved there are no bad groups of Morley rank 3, but we can rephrase it in this form. And then Frank Wagner generalized that and said if H is a simple group, a full Frobenius group of Morley rank H, and H is abelian, and the rank situation between H and G is like this: K Morley rank H, N Morley rank of G, then N has to be at least 2K plus 1. See here in this case where the group has Morley rank 3, and we said it suffices to consider connected complements. then the Morley rank of H has to be 1. In fact, that's easy to see. And this corresponds then exactly to this situation. So in Fréquence example, n is equal to 3, k is equal to 1. And so this generalizes to 3 cannot occur. So the rank has to be actually bigger than that. And this is the setup that we are considering with these geometries now. So we can phrase the results as follows. If you have a connected Frobenius group of finite Morley rank, so in the odd type case, H contains an involution and J is the set of involutions, then these involutions actually form a mock hyperbolic reflection space. And when we call the Morley rank, I mean, if a generic line lambda, if this same inequality that we saw in the previous slide holds, then the group actually splits. And in particular, for groups of Morley rank at least 10, we can say that it always splits, except in 2 specific cases. We could have the situation that G is a simple non-split sharply 2 transitive group of characteristic different from 2, and the Morley rank is either 8 or 10. So, I mean, these examples where Simon André could fit in exactly in this spot. So it would be nice to know that these examples don't have finite Morley rank. Okay, so this is in the odd type case, and in the even type case, so where we have a connected Frobenius group of Morley rank n without involutions. And here we also need to assume, like in the previous case, that H is an abelian Frobenius complement. We don't need to assume that the group is simple or full. So this generalizes this. Then we can say that we have the same inequality, and definitely n has to be larger than 2k. And if it's just larger than 2k, so if it's 2k plus 1, then the group splits. Furthermore, if n is solvable, then we can see that it actually looks like the additive group with the subgroup of the multiplicative group acting as multiplication. So that's the very natural situation then. So when H has no, contains no involution. So now let me say a little bit about the ideas. Let me give you the definition in the purely group version now. If we take a group with a set of involutions, we can think of the involutions as points and the action of the involutions by conjugation as a point reflection. So then we say that this set of involutions forms a mock hyperbolic reflection space if the following 3 axioms are satisfied. Well, we define lines in this way. For any 2 involutions, you look at the set of elements K, set of involutions, such that the product of these 3 involutions is again an involution. So you determine the collinearity by this property. And you ask that any 2 involutions are contained in a unique line. Well, this comes from this definition. Midpoints exist and are unique means that for any 2 involutions, there's a unique involution conjugating one to the other. And if you have 2 distinct lines, there's at most 1 involution conjugating one to the other, one line to the other. So now here's a more complete list of examples. PSL2R acting on the hyperbolic plane. So the non-split sharply 2 transitive groups of characteristic 0 again form a mock hyperbolic reflection space. And we'll see in a moment how to construct these examples from two divisible full Frobenius groups with abelian Frobenius complement. And in general, if you have a uniquely two divisible abelian group and you add an involution, so to speak, from the outside, then you get a mock hyperbolic reflection space consisting of a single line. And this we call the trivial example, but it's nevertheless an important example. And in fact, every finite mock hyperbolic reflection space consists of a single line. So you can't have such an object consisting of more than a line. So let me give you one, in fact, it's not hard, this proposition, but quite crucial. If you have a group with a mock hyperbolic reflection space, then the following properties are equivalent, namely the set of translations, so the set of products of two involutions, can be written as I times j for any fixed involution I. So it means that any product, j times k, can be written as I times k prime. So this is equivalent to saying that the set of translations is an abelian normal subgroup of G, and equivalent to saying that the mock hyperbolic reflection space really only consists of a single line. Of course, you can see that the way lines were defined, they were defined as triples. I mean, they were defined as collections of elements such that if you multiply three involutions in this line, then you go back to having just one involution in this line. So that means that if you multiply four involutions, that is a product of two elements from two translations, three of them form an involution again. So J squared is a subgroup of G. So you see that on a line, you always have that the involutions on the line form a subgroup. So any line forms a mock hyperbolic reflection space in itself. And as a corollary of this, you get that if the geometry just consists of a line, then of course the group splits. So that's an important criterion for showing that the group splits. And the second corollary that you get is that a proper mock hyperbolic reflection space cannot contain any non-trivial projective plane. So in a projective plane, any two lines have to intersect in a point. But this condition here says that if you look at translations on these lines that intersect, you can write them as j times I on one line and I times something else on the other line. So the i's are involutions. So you end up with another translation, again, a product of two involutions, which means that if you have a projective plane where any two lines intersect, you would again have the situation that J squared forms a subgroup, and it would have to be abelian, but it's not, because if you take Ji times Ik, you get Jk, but in the other direction you get something else. So you see that a proper mock hyperbolic reflection space cannot contain a configuration where all the lines intersect. And this is the motivation for generalizing this observation, that from this you see that you don't have projective planes, to see that you can't even have generic projective planes. So what do we call a generic projective plane? We say that a subset of the involutions is a generic projective plane if the Morley rank of the set X is 2k, and the Morley rank of the set of lines that intersect the set X in Morley rank K also has 2k, and then also we want the Morley degree to be 1. So this corresponds to asking that you have a projective plane generically. So if you take a line and a generic line, they will intersect, but you're not asking that any two lines intersect. So, but the observation that I mentioned just before, that you cannot have an honest projective plane in such a mock hyperbolic space, also generalizes in the setting of finite Morley rank to show that you can't even have a generic projective plane. And as a consequence of that, if you have a group where the involutions form a mock hyperbolic reflection space, and it's not just a single line, and n is the Morley rank of n, k is the Morley rank of the lines, you must actually have that n is strictly larger than 2k. And this essentially follows from this observation that you can't have a generic projective plane. And if you had something of this form, it would have to be a generic projective plane. So now we can phrase the statement about Frobenius groups with involutions. So the point is that if you take a connected Frobenius group where H contains an involution, then actually the involutions form a mock hyperbolic reflection space, and all the lines in this space are actually infinite. And when we take K to be the Morley rank of a generic line, then we can conclude that if n is less or equal to 2k plus 1, exactly as in the setting of Fréquence theorem that we saw before, then the group splits. And unfortunately, we can't say anything in the case where n is larger than 2k plus 1. So of course, that's now what we would like to see, what happens if the rank is larger. But now what happens if you don't have involutions? Because I told you this all is based on the geometry that we find on the set of involutions in this group. So in this case, we just add an involution on the outside, and then we work with that one. So, and the reason why that works is that in groups of finite Morley rank that don't have involutions, you often have that they're uniquely two divisible, which is exactly what we need. So let's see, a K loop is a groupoid where the equations AXB and XAB are uniquely solvable for all A and B. So you have left and right solutions. And you have a certain associativity law. It's not fully associative, but it's associative for if you have the same elements here, then you can swap. So this dot is standing for the brackets, not to have so deep nested brackets. I put it that way for all A, B, C, and L. And you want that the inverses behave like an abelian automorphism. So you want AB inverse should be A inverse, B inverse for all A, B in this loop. And because the product is not really associative, we define the precession maps in this way. They look kind of complicated, but the point of them is they're called precession maps, but they could as well be called precision maps because it means they make up for the error term of the missing associativity. So if you have an associative group, then of course A times B times X is the same as, so A times B times X is the same as A times B times X. So here you don't necessarily have that, so you have this precession term that corrects this. And if L is a K loop, then these precession maps are automorphisms, and we set D to be the collection of all, or the group generated by all the precession maps. Now, if you start with a K loop and you end with a group of automorphisms which contains this D of L, so the group generated by the precision maps, then we can define a new group, namely extend L by this automorphism group, and define on this direct product a multiplication in the following form. Well, it's easier to see than to read out, so we multiply them really as a semi-direct product. And clearly the neutral element is 1 and the identity here. And this is important. Inverses are given exactly in this form. So the inverse of an element here is of this form. Now, the next fact that we need, that if you have a uniquely 2 divisible group, then we can define a somehow twisted multiplication in this way. You see, this is why we need the group to be uniquely 2 divisible. And in this way, we can make G into a K loop. So now, a priori, of course, you think maybe it's silly to turn something that's already a group into a K loop, but it's useful in this case. And the integer powers of elements in L are the same in G and in L. So at least in that respect, the groups and the loop structure agree. And if we look at 2 elements in G, then the precision map is given by conjugation with this element. We don't need to remember what this element is, but just to remember that the precision maps are really conjugation by an element in the group. Okay, and I see that I've been running through my slides, so I'm finishing early. Now, if you take a connected Frobenius group of finite Morley rank without involutions, and assume that H is abelian, then we set N to be the Morley rank of G and K to be the Morley rank of H. Then, because G is uniquely 2 divisible and centerless, we can define this K loop just as before, and we define an additional automorphism of this loop by this automorphic inversion. Then, of course, this automorphism is central in L, and in particular, we see that this G times E is a subgroup of the automorphism group. And now, from everything that I showed you before, we see that we can, from the group that had no involutions, we constructed this K loop, and we make this thing into a group. And the set of involutions in this group now, from the previous slide, if you remember, is of this form L times this pair 1 epsilon. And hence, you see that the Morley rank of the set of involutions is exactly the Morley rank of the group that we started with, because L essentially is the same underlying structure, just with a twisted multiplication. And so the rank of J is the rank of G. And now what one can see is that if, again, this is a full Frobenius group, then this is actually a mock hyperbolic reflection space. And all the lines of the rank, all the lines in this reflection space have Morley rank K, and it translates of this H. And if we don't assume that it's full, well, then we have the same distinction between a projective plane and a generic projective plane. That is, we only get that J forms a generic mock hyperbolic reflection space. That is, we only have generic lines. Not all pairs are contained in a line, but generic pairs are contained in a line, and the rest remains the same. And so we can state the following result. If we have a connected Frobenius group of Morley rank n without involutions and with an abelian Frobenius complement of Morley rank k, then we know that n is strictly larger than 2k. And in the case where it's exactly 2k plus 1, then the group splits. And in case n is solvable, then we see that it actually splits in this form as the multiplicative subgroup of the multiplicative group acting on the additive group. And so it's the standard example of a Frobenius group. Okay, so I see I went way too fast, but anyway, I'm finished. Thank you.
Okay, thank you very much. And so if there are some questions, now we have a lot of time for questions.